Good morning, everyone. Warm greetings from the Department of Civil Engineering, Adi Shankara Institute of Engineering and Technology, Kaladi. It's a great pleasure and honor to welcome you all to this technical webinar on seismic design of buildings and introduction. First of all, let me welcome Dr. K. Dhanashekhar, Professor and Head of the Department, to the session. We are honored to have such a distinguished group of teachers and students joining us for this webinar. Welcome you all. Now, let me take a moment to introduce the resource person for today's session, Mr. Preet K. Laurel. He had completed his BTech in Civil Engineering from SCMS School of Engineering and Technology and started his career at Shapoorji Pallonji Corporation Limited. After completing his MTech in Structural Engineering from College of Engineering Trivandrum, he worked as a design engineer at SACPAL. He had also worked as a senior structural engineer at Build Next Kochi. Currently, he is working as a design engineer at Lera Consulting Structural Engineers, Mumbai. Sir, welcome to the session. Handing over the session to you, sir.
Can we begin?
Yes, sir, we will begin.
Okay. Thank you, Rima ma'am. It's always a pleasure to come back to colleges of any sort. So, welcome you all. Welcome to all the participants and teachers. So, the topic that I chose for this day is seismic design of buildings. It is a very basic introduction to all of you. I really don't want to bore you with all the very technical stuff. So, as Rima ma'am said, I'm right now working as a senior structural designer in Leslie Robertson Associates Mumbai. It's a multinational company. So something that really is very exciting to tell you guys is that all companies always prefer to take freshers in. So if you're really interested in structural engineering, and if I know that there will be so many here who are really interested in structural engineering, don't hesitate to target very big companies first. We all think, let's go to small companies first. Never like that. You can make a list of all the best companies in the world, send your resumes, aim big, and start like that. So, moving on to my presentation. So, before jumping onto this specific topic, I like to start with a story. This is one of the most, uh, let's say, it's one of the most exciting and it's a very interesting story because you will understand why. This story has shaped structural engineering in many ways, and it's a very recent one too. So this right here is the City Cop building in Manhattan, New York. It's a very beautiful building, as you can see. It is 59 stories. And if you look on the left side of the screen, you'll see a pyramidal shaped building. That's the St. Peter's Church of Manhattan. Now, this is a very old church, and this church has a lot of basements. In order to accommodate this church in this location, they had to go to this design. That is, all the 59 stories are actually starting way above the church. And the whole building is supported on these huge 9-meter tall steel columns. So basically, this is so complex because the structure itself is not symmetric. This is the actual photograph of the structure from quite far. If any of you ever get a chance to go to New York someday, you can see this building even from your aircraft before landing. It's that phenomenal. So there is a 45-degree crown on top, which causes all the load, the biggest loads to be on one side of the building. Now, interestingly, it's not the shapes or it's not the lack of symmetry or the stills that makes this building interesting. What makes this building interesting is the fact that it almost collapsed, killing maybe millions of people. So yeah, the small photograph on the left shows you how the stills are placed so that it is not clashing with the church. This potential catastrophe was in fact avoided by a grad student, someone like one of you. So it is her photograph that I kept here because I felt that only her photograph is relevant here. So there are three people in this story. The first one is William J. Lemasharian. He's the person who designed the building. He's a very famous structural engineer. He designed the building and the construction started in 1970. The building is completely in steel. So there is, like you saw in the earlier images, there are 9 meter tall steel columns, and then there's a central steel core that goes all the way to the top with a tuned mass damper on top. Now let's not go into all those technicalities. It took them 8 years to finish this building. So by 1978, the building was done and it was occupied also. It's a complete office building. And it was a pride of New York City. It was a pride of New York Municipality Corporation. Everybody was very happy with the building. The amount of steel used in the building was also fairly less than half of what was used in the Empire State Building. So it was economically good for the city also. So everybody praised Mr. William J. Lemonster. So it was all good. Everything was going well. And then this lady, Diane Hartley, she actually chose to study this building for her graduate BTech project, BE project. And while doing the project, she had a lot of questions. So she was always asking her guides, why, how can such a unstable structure stay on top of hills? What happens with the earthquakes? What happens if there's a strong wind? So she kept on asking all these questions to a point where the guide was actually starting to doubt himself because he did not have all the answers to him. So he told her, why don't you directly connect to Mr. William J. Lemishria? And he arranged the same. So one fine day, Mr. William gets a call from Diane. So Diane asks him, sir, I have a lot of questions. After a while, Mr. Lemishria understood that he was not confident in the design that he did. And it sort of offended him. So he said, see, it's not always what you see on the textbooks. When you analyze and design things in the real world, you'll see that there's a lot of difference. So you have to take in the elements of practicality. So he kept on talking all these things, defending his own design. And the call ended likewise. But what happened was that after this call, Mr. William J. Lamasteria could not speak. He started doubting his own calculations. He went back to his design. He started checking them A to Z. And finally, he found a major flaw. It was that in all his calculations, he considered all the connections to be welded connections. But at site, due to some difficulty in doing welding, in majority of places we had opted for bolts and not welds. This at that time, this was not considered as a big difference. They said bolt, weld, what difference would be there? And they went on and drilled a hole. But now, when he calculated the total wind force coming on the sides of the building in the event of a storm, he came to the conclusion that the building will 100% topple, crashing itself, killing all the people in it as well as the people in the neighboring buildings. So this is enough for someone to go mad, right? So he just ran out of his home. He has a secret residence in some island. So he went there, he stayed there for a long time alone. He was contemplating what to do. He was contemplating if he should kill himself. So he went through a whole lot of personal mental trauma. Finally, he gets this realization that if he solves this problem, he's going to save millions of lives. So that gave him the courage to come out and speak. So he goes to his close friend, Mr. Leslie E. Robertson, who was the founder of our company. And Leslie E. Robertson is also the person who designed the Twin World Trade Center towers were uh, that came down in the 9/11 terrorist attack. So Mr. Leslie Robertson corroborated Williams' calculations. He also was assured that there's a major flaw. Two people went to the New York Municipality Corporation. They told them the error. They even gave them the fix. And the corporation took this up positively. They repaired the whole building. They did not change, they added steel plates to all the bolted connections. They welded it in every joint, they added plates, welded plates. They made all the joints stiffer. They spent a whooping $9 billion and repaired the whole building to safety. Now, how did all this happen? All this happened because a graduate student did not hesitate to ask questions. So that is the power that you all hold. Your questions may sound silly to yourself, but it might not be. It might change the world someday. So there is nothing as a silly or stupid question when it comes from a graduate student. Keep on asking questions, keep asking questions to your teachers, to your peers. Talk to as many people as you can from the industry so that things like this can happen. Okay. So with that, I'm moving on to the topic. So you know how earthquakes act, right? So there are two types of earthquake waves. The first the image on the top, you can idealize that as maybe 10 people standing in a queue and one person pushing from the back. So you know how that push will go, right? So that is the first type of waves. The second type of wave is like so many toys on a bedsheet and you whip the bedsheet. So these toys will all go up and down. So it is a combination of these two actions that come to your structures as a seismic wave. And there are so many characteristics for a wave that determine the impact or the amount of error that the amount of damage that your building can withstand. Let's not go into all those deep things. Now, I don't know how many of you will recognize this image on the right. If any of you do, please speak up. There is something called natural frequency. It's the frequency at which a system will oscillate in its maximum amplitude. Okay, so this is an episode from one Tom and Jerry episode where Tom is sleeping on a hammock and Jerry actually sends a whole train of ants to climb onto the hammock. If you remember this episode, you can remember how Tom's hammock eventually collapses because of the resonance created by these ants. And that is how dangerous natural frequency is. In order to understand this concept once more, I want you all to Google what I've written below, Tacoma Narrows Bridge collapse. Many of you would surely be familiar about this. If you're not, please Google this after this webinar. It's a very interesting read. And to speak further on natural frequency. So you've all seen ships, you've seen boats, you've seen aquatic vessels of all sizes. When an object vibrates at a frequency equivalent to its natural frequency, the vibration of the amplitude increases significantly, which could lead to irreplaceable damage. So this one thing called resonance is something that all engineers are terrified of. I'll tell you why. Let's imagine that we have a huge ocean and there are small ships and then there are huge ships. So a very small wind comes and there are small waves in the water surface. What happens to the small ships? The small ships will all go up and down side by side. It will rock all the small ships. But the big ships won't even know that these small waves are coming. So you can idealize this to buildings. So when there's a small earthquake activity, when the time period of the earthquake is very small, and when it acts, all the tiniest buildings, the houses and all, with time period less than 1 second, will be affected. The medium-sized buildings and the tall buildings will not be affected, similar to your ships. On the other hand, if it's a huge storm and then there are tidal waves, what does the small ships do? The small ships can easily carry themselves over these huge waves without causing any damage to themselves. Whereas the big ships will all sway really violently. It could even topple the big ships. And that's what happens when earthquakes of huge time periods strike. Your small buildings will be saved, but your larger buildings will oscillate vigorously, causing structural damage. So this is how the natural time period of a structure reacts to the natural time period of the incoming earthquake. And this is something that we cannot always predict. So in history, in 1985, there was an earthquake in Mexico City. And interestingly, only structures from 1 to 5 stories were damaged. All the ground level structures as well as all the tall skyscrapers were not touched. This building on the right actually withstood the earthquake without any damage at all, whereas there were 5-story buildings that completely toppled down. So that is the impact of the natural frequency concept and the concept of resonance. So don't be scared by this equation. This is the equation that determines how much seismic force is going to act on your building. As you can see, there are some parameters in this equation. We'll go through them one by one. First is the zone factor, which is Z. Then we have the ground acceleration, which as a whole is SA by G. Then we have the response reduction factor, and then we have the importance factor. These four parameters together decide how much force is going to act on your building. So this is the force that we use to design our structure so that when this earthquake strikes, this is a theoretical earthquake, maybe the worst earthquake, which would probably come in the lifespan of the structure, not necessarily. So let's go through these factors one by one. Zone factor is the factor that is determined by the location of your building. So I'm sure that you all were alive when the Bhuj earthquake happened in 2001, I think. So when that earthquake struck and many structures were critically damaged in Gujarat, many lives were lost. The Indian government and the Structural Engineers Association realized that some revisions were necessary because until then, India had never faced any earthquake that caused so much structural damage. So what you see on the left is the previous code, that is the IS 1893, 1987, I think. So if you see on the map on the left, you can see many white areas. And on the legend, it is shown as zone 1. So these white areas are all minimal earthquake prone. Now, in the latest code, which is IS 1893 2016, all these areas are eliminated. And the coding system starts from zone 2, which means all the areas that were previously assumed to never have earthquake activity are now considered to have minimal earthquake activity. And all of us, I'm right now in Mumbai, most of you are in Kerala. So we all are in zone 3. Zone 3 means there's some chance of seismic activity which may not be major. And then we have zone 4, which is the orange colored areas. That is almost all of Jammu and Kashmir, Delhi. And then the zone 5, which is the critical areas, north of Gujarat, northeast, and some parts of the Himalayan regions. So based on where your structure is, this zone factor, if you remember in the first equation, it was in the numerator. So the more critical your zone, the more force will come onto your building. And if you see the two islands, Lakshadweep and Andaman, they are in two different zones. Lakshadweep is in zone 3, whereas Andaman is in zone 5. That is because Andaman and Nicobar Islands are actually mountainous islands and they even have volcanic activity. So they are considered to really be prone to earthquake. Whereas Lakshadweep is coral islands. The second factor called the ground acceleration coefficient depends on the type of soil on which your structure is resting. So we can divide the soil strata, not the strata, the type of soil into three different. Soil type number one will be the rocky or hard type soil, which is the best for structures. Soil type number two is medium or stiff soil. And soil type number three are soft soils. So you would have heard all these terms in your geotechnical classes based on all those indexes and plasticity and all those parameters that you've learned. The geotechnical experts will do soil testing, they'll do geotechnical exploration, and then they'll come out with a report that tells us structural engineers that what type of soil is expected in the site where the building is going to be constructed. So let's assume that the type of soil is type 2. Okay, just an assumption. With that data which we got from the geotechnical expert, we go to the graph. This graph from the zone code 1893 is a graph between the ground acceleration coefficient and the natural time period. So once you have the natural time period of the structure and the type of soil, so you can see that the medium soil is shown by a medium thick line. So just assume that our structure has a time period of 2. So it is actually, if you can see my cursor, it is actually standing over here. Okay. So if it was resting on soft soil, the ground acceleration coefficient would be 0.5. If it was resting on medium soil, it would be around 0.75. And if it was resting on hard soil, it would be around 1. What does that mean? It means that there is a difference of around 50% between soft soil and hard soil. So if you have the same identical building in two locations, and one location has hard soil and the other location has soft soil, the structure in the soft soil will have 50% more earthquake force acting on it. So that is how important the geotechnical investigation is. The next factor is the response reduction factor. So this is a fairly technical term, and I will just put a snip of the very first few points from the table. This is actually a very long, huge table with a lot of points. So you know that the basic construction or the conventional construction of building is putting column, beam, and slab. That is the conventional system. And based on the type of reinforcement detailing, the way the stirrups are tied, the way the top steel and the bottom steel of beams are placed, the spacing in the column hoops, all these things decide whether your structure is an ordinary structure or a ductile structure. That is something which is specified by another code, which is specific for ductile detailing. So, uh, when you have two buildings with the same sizes of columns and beams, you can detail one building as an ordinary building and, and the other building as a ductile building. If you see the first one, that is moment frame systems, A, RC buildings with ordinary moment resisting frame. So whatever we have seen so far in the sites that are around your homes, the simple structures are all ordinary moment resisting frame structures. So what is the response reduction factor given there? It is 3. Whereas when it's a ductile building, that is RC building with special moment resisting frame, the response reduction factor becomes 5. Now, if we go back to the main equation, you will see that R value is in the denominator of the equation. That's why it's called response reduction. So if your R value is 5, that means the whole force is being divided by 5. If your R value is 3, it is being divided by 3. So the greater your R value, the lesser is the force coming on your structure. So what does that mean? That means that if you put some extra effort, if you put some extra money and resources to do ductile detailing in your beams and columns based on IS 13920 code, you can actually reduce your seismic force coming in the structure. So who decides what to do? That is where the structural engineers come in, based on the zone. So let's say that my building is in zone 4. If it's in zone 4, that means there is a really big chance that an earthquake will strike during its lifetime. So as a structural engineer, I would definitely suggest the clients to prefer ductile detailing, that is special moment resisting frame. From the client's point of view, it means that they'll have to put in some more money because some additional steel will come, some additional labor will come. But on the overall, the amount of force that I will use to design that building will actually be slightly lesser. So in turn, that will again reduce my actual steel. So that is a balance that we'll get to know once we do the whole process. And then we'll find out that how much is the total cost of the structure. On the other hand, if we blindly go for an ordinary moment resisting frame without ductile detailing, the seismic force will be huge and definitely the amount of steel will actually be high. But the detailing will be simpler as such. So that is the balance coming here. Then, if you look at the second part, that is brace frame system. So bracings, I think you would have definitely seen images of building with bracings, maybe X-shaped bracings on the sides. So these systems are always very helpful in resisting the lateral loads, be it wind or be it the seismic forces. Now, just look at the very last one, load-bearing masonry buildings. Most of our homes in Kerala will be load-bearing masonry buildings ba- made out of bricks, right? So the response reduction factor is only 1.5, which means that if a seismic activity strikes, our masonry structures might not withstand that. There is not much force to be reduced even in the actual calculation. That is why when it comes to seismic design, we don't even look at masonry buildings. Means it's an assured case that they'll all fail. So that is why reinforced concrete structures play a vital role in all seismic designs. And then we prefer ductile buildings because ductile buildings are better in behavior when the actual earthquake strikes. So yeah, if you read the question I posted on the left, how much energy can the structure dissipate? So it is this question that determines the R values. So a ductile building, because of its ductility owing to the special type of reinforcements, can actually oscillate more without breaking when the earthquake strikes. And due to this ability to dissipate more energy, we can actually give a huge denominator in that value, a denominator of 5, and reduce the actual earthquake. I hope you got some idea to it, and I don't expect you to understand this completely because anyway, I'm only showing you 3 out of maybe 7 or 8 parts of the table. Another question. So, which structure do you think is more important? Is it a school building or a 40-story residential structure? Can anybody answer me? If you are shy to speak up, you can put it in the chat box also. Let's assume that we have a 40-story residential building. There are maybe 2,000 people living in the building. And then there's a school nearby. The school has it's a small school, maybe 300 to 400 students are there. So which building is to be considered as important in the point of an earthquake? What happens is that when we think about it, a huge residential building with 40 stories and maybe 2,000 inhabitants seems to be more important than a small school building with 400 students. It's not actually the number that counts. If you have been following the news of what happened in Wayanad, you can see that it's always the schools, the public places, the government offices. Am I audible? Something happened to my mic.
Yes, sir, now audible.
Okay, yeah. So as I was saying, if you've been following the news, you'll see that it's always the schools that serve as rehabilitation centers. In the event of an earthquake, people would always rush to the nearest school or the nearest hospital or the nearest maybe a public auditorium. So places like these of social and communal importance are always considered to be way more important than residential buildings or office buildings, which may actually house more number of people. That is because post a catastrophe, these buildings actually serve as places of rehabilitation. So if you read the first paragraph from this table, important service and community buildings or structures, for example, critical governance buildings, schools, signature buildings, monuments, emergency buildings like hospitals, telephone exchanges, radio, railway station, airport, fuel stations, fire buildings, community halls, shopping malls, all these places which could see crowding of people after an emergency are considered to be the most important structures. So for these, all these critical buildings, we have an importance factor of 1.5. Then you have your residential buildings. So if your residential building has more than 200 people, the importance factor is 1.2. And if there are less than 200 buildings, and for all the other structures, it's taken as 1. So if we go back to our key equation, it is it is the denominator of the fraction on your denominator. That means it will come to the numerator. So greater the importance factor, greater is the force that will be taken into your design. There's also one more thing to this. So these are actually suggestions that the code gives us. Now, if you intend to build, you become a builder and you want to build a 20-story building to house maybe 200 or less than 200 people, 150 people, let's say. It is always the client who can actually consult the structural engineer. The structural engineer can be told that I need to do my building with an importance factor of 1.5, right? So then obviously the amount of force coming on the building, considered force would increase. The cost of the building will increase, all the columns, everything would become bigger. So these suggestions are the bare minimum. You can always do better than this. That doesn't mean you go to importance factor more than 1.5. 1.5 is your maximum. But I'm saying that if the code says that you need to follow 1.2, you can follow 1.5 as an added step, as an additional factor of safety. So let's round up this equation once again. We have the zone factor that is coming from where your building is located. Then we have the ground acceleration factor, which is determined by the nature of the soil and the geometry of the structure. Why did I say geometry of the structure? Because the x-axis of the graph was time period. Then the response reduction factor that depends or that is determined by how ductile are we planning to make your structure. And finally, we have the importance factor or how important the structure is or how important do you want the structure to be. So based on all these parameters, we get the value of the horizontal seismic coefficient AH. And this value is actually a value in force. It is the base shear force. So that force is used to design the building, analyze the building manually or using software or whatever. This is actually the result of all these key elements that come into your picture. So if somebody ever asks you, if they show you a building and ask you, do you think this building is seismically prone? You need to ask these four questions. You need to find out where the building is. You need to find out what type of soil is below the building. You need to find out the geometry of the structure. How tall is it? What would be the natural time period? You need to find out what type of framing has been done in the building. Like, are there beams and columns that are normally designed or are those ductile? And also, what's the function of the building? Does it serve a communal or socially responsible function, or is it just a residence or an office? Based on which you can come to the importance factor. Clubbing all these values together, you get your base shear coefficient, and then you know what force has to be considered for the lateral resistance. So this is all that I intended to talk on the topic. I would also like to add some additional points. The ideal civil engineer is a man who knows everything about something and something about everything. This is something that my boss always used to tell our team. So when we, after your BTech, some of you might go to MTech, some of you might go to some other fields, you might do your master's in business. So there are a million options to civil engineers. So one thing that you should always know if you stay in the field is that a structural engineer is not someone who knows only structural engineering. A structural engineer has to know structural engineering, but he should also be aware of all the other fields. Same goes to the environmental and geotechnical engineers also. So that is where your BTech degree comes into picture. What all the subjects that you have are equally important. It is never that one is more important than the other. And I'll just show you some case studies which prove this one small simple sentence. So both these buildings, one on the left is the Vidara Hotel in Las Vegas, excuse me, and the one on the right is the Walkie Talkie building in London. So the architects designed these buildings to be very cool, futuristic designs. But if you look at the buildings, both these buildings are actually shaped like concave mirrors. And we all know what happens when you place a concave mirror in the sun, right? It focuses all the sunlight to one point, and we can actually burn paper or little bits of things with the small concave mirrors we get. I'm sure that most of you would have done it at home. Even with a magnifying glass, it works. So this is something that these people did not foresee. And once they glazed the whole structure, there was a swimming pool in front of the Las Vegas hotel. The water became so hot that nobody could go near it. And in London, somebody actually parked his priced Jaguar in front of the walkie-talkie building. And it was a normal sunny day for London's standards. And the car actually melted. All the sunlight got focused to the roof of this Jaguar and the roof melted. Later, there were a lot of protests because it was creating, obviously, it's going to create a lot of problems, right? People actually started cooking on the tarmac in front of the walkie-talkie building. They would just break eggs onto the tarmac and they'll make omelets out of it. So those were the type of protests that were happening in front of this billion-dollar project. Eventually, the owners had to shade off the entire front fascia with an additional cladding that was not reflective, ruining the whole look of both these buildings. And I think, let me just, yeah, the London building. The in the walkie-talkie building, it was also creating a vortex effect. That is, the wind concentration in front of the structure was so high that it was, knocking off signs, even bicycles around. So what's the lesson that we learned here? The structural engineer did his job very well. Everybody did their jobs very well. Even the architect came with a very modern building that nobody has seen before. But what everybody failed to do was go back to the standard and think about what they did then. So it is that basic lack of basic understanding from maybe everybody involved in the project. I would not directly go and blame the architect. This is something that even a normal person would understand when they see the issue. But to foresee such issues, that is where your judgment always comes into picture. And I'm sure that if such an idea was given to maybe school students, they might in fact actually consider this case because they are familiar with the container and all the pranks that they do with it. So that is where the common sense factor becomes more important than every degree you earn or every billion of dollars that you spend. This is the Kemper Arena complex. This is in USA. So what happened is it's a huge stadium. It hosted a lot of matches. Everything was going well. One fine day, it was raining so bad and the whole roof collapsed. Luckily, it was when there was no match happening, so no lives were lost. Now people started wondering, like it's a $1 billion project. How can the roof collapse? Who? They were all pointing fingers. Was it a structural damage? And then obviously there will be an investigation team. And what they found out was it was the lack of sufficient number of drains. Quite silly, right? So the whole structure, based on its area, based on the local codes, it should have had 16 storm drains. But to accommodate storm drains in building is always an ISO, right? So architects don't want to see drains coming out of all the places. So they reduced the number and they just gave six, I think eight. Yeah, eight drains. They reduced the requirement to half. So what happened when there was a very big rain? The accumulation of water on the rooftop just became so much. The load became way more than what the structural engineers anticipated. Even the factor of safety that which we all depend on so much could not help us enough, and the whole roof just crashed in one instant. So who's to blame here? Because the people who decided to maybe ignore the code and say 16 is too much, we'll just go ahead with it. And so the structural engineer at that point would always say, no, it's not my fault, it is their fault. But in the end, it is the building that suffers. Right? It's the outcome of all the engineers is to create a stable, sustainable structure that stays for a long time and serves its purpose. If that is not met, then there is no point in pointing fingers and blaming each other. So even in our structural firm, we get drawings to review from mechanical, electrical, and plumbing teams. So they give us their drawings, and I really did not understand the purpose of doing that. I always felt this is not my job. Why should I review plumbing drawings? But then I could see my boss finding out major structural flaws from the plumbing drawing. He would come to us and show us that you see these two pipes are going through one of our critical beams. So he gave this pipe, they would drill through our beams, making our beams unstable. We have to ask them to reroute their plumbing. Such things comes because he has experience of a lot of years and he knows that where the critical issues might arise. We, on the other hand, we are all naive. We are new to the field. So we might feel that we as structural engineers, we'll do this job. Let the plumbing guy, let the MEP guys do their job. So it is never like that in our field. That is both the blessing and the curse of a civil engineer. We have to work hand in hand. At the end, we have to even depend on the unskilled labor who's mixing concrete at site because his work is also equally important to our work. And finally, this is John Hancock Tower in Boston. So it's a beautiful building. It was structurally perfect. There was no problem from any point of view until it became summer. So when it became summer, due to the heat fluctuations, something that the facade engineer. You might not be familiar to that term. FACADE engineer. Facade engineer is the guy who designs these huge glazings. It's not an easy task because these glazings that you see are it's all very polished and thin and very tall, right? So all the winds that the structural engineer is considered to act on the building actually acts on the facade first. So the facade engineer has to design all that structurally. He has to analyze it. So he has a whole complex job to do. What he forgot to do was consider the impact of temperature variation. So when summer came and there were temperature fluctuations, what happened was the glasses began to crack. Imagine such a tall building and the glass windows are falling from such heights. It would kill the people walking on the streets below, right? There were so many accidents happening in the coming days. Many people were injured. I don't know if anybody were killed, but many were injured. Many vehicles were damaged. These huge shards of glass were falling from the skies. And they closed off the entire street and repaired the whole building. They had to replace each glass panel with a different panel that had a tolerance to expand and contract based on the temperature fluctuation. You can imagine how much would that have cost. So these are all results of small negligence from somebody involved in the project. And since civil engineering is always a huge team effort, someone's error can cause problems to the whole team and to the end user also. So that is all. With that, I come to the end of my presentation. If you have any questions, please be free to ask. This is my email ID. You can always contact me on email also. If there is any slide you want me to go back to also, we can do that. We have time.
Sir, how can we enter
Okay.
this industry?
Structural engineering, is it?
Yes,
Yes. Okay. So yeah, thank you for the question. So one thing I need to tell all of you very specifically and strongly is that do not take an MTech degree if you are really not keen to, if you're really not passionate enough. I have a lot of friends who just took MTech because it had a stipend. Don't do that, please. Don't do that. You'll be very sorry in the future. If you don't intend to work exactly in the field, in the core field, please don't go do your MTech just for the sake of it. There are so many other things that you can do after your BTech. And if a BTech person has 15 job opportunities in front of him, an MTech person would definitely have less than that because
There are feedback ning
his specialization is specific. So to answer your question, uh, structural engineering ഇഷ്ടമാണെങ്കിൽ തീർച്ചയായിട്ടും take an MTech in structural engineering, but take it from the best college you can find. Okay? Master's degree മാസ്റ്റേഴ്സ് ഡിഗ്രി ഏതെങ്കിലും കോളേജിൽ നിന്ന് എടുത്തിട്ട് അത്ര കാര്യമില്ല. You need to have a brand value for your master's degree because huge companies always prefer the tier one colleges, IITs, NITs for their fresher applications. Once you gain, even if you study from a normal college and you gain good experience, then you can work anywhere. I did not study from a very high-fi college. I did not go to IIT and all, but after a course of time, after gaining 5 years of experience, I felt that I was ready enough to go to the big guns. I applied to a million companies. Nobody even opened my resume. But then luckily, one fine day, I got selected in Lera. I cleared the tested interview and then I joined it. So it takes time. Means you can always reach your dream companies eventually. But that road is easier if you have a brand value in your college. So right now, you're all in your final year, I'm assuming. So focus on your studies, uh, get very good grades, get a good gate score. And with that, right away, you can apply to all the best companies in the field. Open LinkedIn, open Google, make out a list of all the best companies, the top companies in your field. Talk to people who are working in the field because what you learn in college is not what is happening out in the field. So when you sit in your classroom and learn structural engineering, maybe you'll like it, maybe you'll hate it. But even if you can't judge your job based on your course. That's what I'm trying to say. So you talk to people in the field, you ask them what they do in a day, you ask them how their typical weeks are, you openly ask them how much they are earning. Means we can always say that job is important, but money is equally important. We are all working for money. And stop comparing yourself with the IT fields. Okay, so that is something we civil engineers always do. We always keep sulking, saying that the IT guys are earning more. But our field is different. Our field is not the same. The returns in our field are also not the same. So do not look at other fields. Uh, but then you can always find a job in the top companies, and definitely you will get very good salaries. And be open to shifting also. Do not stick to your hometown. You should always be open to go to new places, work in bigger companies, gain exposure. So what I've seen is that we always, even during your BTech, I'm sure that most of you would have done internships also. We would all choose, companies in Kerala, companies locally. Even I did the same thing. But now that I'm in Mumbai, I see that the children here, when they have a chance to do internships, no, they actually apply to companies in Delhi, they apply to companies in China, and some of them actually get it also. And they go there, they get paid for it. So companies prefer interns too. Interns are always welcome in all the big companies. The small companies might not prefer them, but the big companies always love to have interns. You need to show your worth. You need to write a good cover letter, apply to internships. You can gain experience even during your BTech like that. So that's it. So once, if you're sure that you want to be a structural engineer, do the best for that. Choose the best college, get a very good grade score, aim high, aim big. That's it. Same goes to all the other fields also. Okay, I'm talking about structural engineering because that is only one thing that I know. But I have friends who've done environmental, transportation, geotech, and they're also all working in very good firms. A friend of mine finished her BTech and then she did her master's in transportation engineering from NIT Trichy. After that, she got placed in L&T Chennai Transportation Wing, and she was earning quite well there. She worked there for around 5 years, and she directly applied to transportation company in Canada, and she got placed directly in Canada. She did not have to go through all the trouble that the others are going to, eventually reach Canada. She directly got a PR, and she just flew with her family. So that is how cool our field is. We have a lot of opportunities. It's just that it's not as evident as the other IT field. So you need to search, you need to do your hard work, you need to create a list of your own. And there are offbeat courses also. There are courses in IISc Bangalore, in climate science, in water resources, in renewable energy, in earth sciences. So these are fields that would really be interesting from a research point of view. If your aim is to do a master's, then go to a PhD and become a research scholar. Do something that everybody else is not doing. Find the rare courses. There is ocean engineering in IIT Madras. Ocean engineering is the study of oceans and how civil engineering can, help oceans. Going to all these underground, underwater designs, rig designs, offshore engineering, all those come into picture there. IIT Madras is also designing underwater vessels, the type of things that you see in the, you know, Marvel and DC movies. So there are actually civil engineers working there in the team. So go to the cool things, find out the coolest things that you can do. If I'm talking about research, if research is your aim, go to the coolest thing because there are already so many people doing the conventional things. We don't need more people doing conventional things. I hope I answered your question.
Yes, sir. Thank you, sir. Thank you very much.
Yeah.
Okay, thank you, sir, for your valuable session. On behalf of Department of Civil Engineering, Adishankara Institute of Engineering and Technology, I extend my sincere gratitude to you, sir. Also, I thank our HOD, Dr. K. Dhanashekhar, for his guidance and support for conducting this session. Participants, thank you for your active participation. Thank you.
Thank you.